Some of the most brilliant cosmic objects are blazars. They're made up of a supermassive black hole that can produce two strong jets perpendicular to the disk and feed off material spinning around in the disk. When viewed through our telescopes, a blazar seems unusually bright because one of its potent jets of fast-moving particles is directed directly at Earth. Do you know how these jets' accelerated particles generate such high energies? Hello science lovers, welcome back to Theory of Science. Without further ado, let's get into it. Don't you guys want to know what a black hole is? The astronomer from MIT and their associates have identified a potential source for the signal. The signal, AT2022-CMC, most likely originates from a relativistic jet of matter shooting out from a supermassive black hole at speeds of close to the speed of light, according to a study published in Nature Astronomy. They postulate that the jet resulted from a black hole that unexpectedly started consuming a nearby star, releasing a tremendous amount of energy in the process. The source is also the farthest TDE yet discovered, located more than halfway across the universe at a distance of 8.5 billion light-years. Other instances of this tidal disruption events, or TDEs, in which passing star is shattered by a black hole's tidal pressures, have been seen by astronomers. AT2022-CMC is brighter than any TDE discovered to date. How is it possible for something so far away to be so bright in our sky? According to the team, it's possible that the black hole's jet is pointing directly at Earth, which would make the signal appear brighter than it would if the jet were pointing in the other way. Doppler boosting is the effect that sounds like a passing siren amplified. Understanding these mysterious forces that operate in and around a black hole, forces that are present even though the black hole is invisible to the naked eye and have the power to destroy the worlds around it, has long piqued the curiosity of astronomers who are interested in unraveling the mysteries of the cosmos. Scientists from NASA Goddard Space Flight Center conducted 100 complex simulations to examine jets, which are fast-moving narrow beams of intense particles that originate from supermassive black holes. These gigantic objects, which can weigh millions to billions of times as much as the Sun, are found near the centers of active galaxies that are still forming stars, such as our own Milky Way galaxy. The NASA Center for Climate Simulations Discover supercomputer was used by scientists to carry out the extremely complicated simulations. The process by which these jets grow to be so bright has been explained using information from the Imaging X-ray Polarimetry Explorer, or IXPE, observatory. They discovered that shockwaves leaving the black hole move at supersonic speeds, energizing subatomic particles known as electrons. Ryan Tanner, a postdoc in NASA Goddard's X-ray Astrophysics Laboratory and the study's lead author, said that as jets and winds emanate from these active galactic nuclei, or AGN, they regulate the gas in the center of the galaxy and affects things like the star formation rate and how gases mix with the surrounding galactic environment. For our simulations, we concentrated on less well-studied low-luminosity jets and how they affect the host galaxies' evolution, according to Tanner. On the computational analysis released earlier this year in the Astronomical journal, he worked with X-ray Astrophysics Laboratory astrophysicist Kimberly Weaver. Observational proof of jets and other AGN outflows first emerged from radio telescopes and then from X-ray telescopes operated by NASA and the European Space Agency. Weaver and other astronomers have been piecing together an explanation for their origin over the past 30 to 40 years by combining optical, radio, ultraviolet, and X-ray evidence. According to Tanner, high-luminosity jets are simpler to locate because they produce large structures that may be seen using radio measurements. The astronomy community is not as knowledgeable about low-luminosity jets as it could be since they are difficult to observe and research. The simulations powered by NASA's supercomputer by Tanner and Weaver employ the entire mass of an imaginary galaxy around the size of the Milky Way to establish realistic starting conditions. Spiral galaxies like NGC 1386, NGC 3079, and NGC 4945 were studied for their gas dispersion and other AGN features. Tanner altered the Athena astrophysical hydrodynamics algorithm to examine how the jets and gas interact with one another over a distance of 26,000 light-years, or roughly half the Milky Way's radius. The researchers chose 19 simulations for the whole set of 100 simulations, which required 800,000 core hours on the NCCS Discover supercomputer. Instead of having to employ more limited resources, Tanner said, quote, "Having access to NASA supercomputing resources allowed us to investigate a considerably broader parameter space," end quote. This resulted in the discovery of significant linkages that would not have been seen with a narrower scope. So guys, if you want to escape that black hole, well, you can do so just by clicking that subscribe button. Just kidding, you can't actually escape a black hole. If you're enjoying the video, please like and share it for more exciting videos like this. Turn on the bell icon to receive notifications about upcoming videos. Now, moving back onto the video. Two main aspects of low luminosity jets were shown by the simulations. First, they interact with their host galaxy significantly more than high luminosity jets do. They are able to take on a wider range of shapes than high luminosity jets because they both influence and are impacted by the interstellar medium within the galaxy. Weaver said, quote, "We have shown the mechanism by which the AGN hits its galaxy and generates the physical properties, such as shocks in the interstellar medium, that we have observed for nearly 30 years. The comparison between these results and optical and X-ray data is good. As a PhD student studying AGN, such as NGC 1386, I was surprised at how well the theory matched observations and answered persistent questions I had about them. Now that we have more time, we can use bigger samples," end quote. A shockwave within the jet, according to a recent study published in the journal Nature, is the most plausible explanation for particle acceleration. We've solved a mystery that's been a mystery for 40 years. The puzzle pieces were all in place at last, and Yanis Leodakis, the study's lead author, stated that the picture they painted was crystal clear. The scientists investigated an unusual phenomenon known as a blazar at the heart of a massive elliptical galaxy called Markarian 501, which is about 460 million light-years away from Earth and pointed in the direction of the constellation Hercules. The distance travelled by light in a year is 5.9 trillion miles, or a light year, which is 9.5 trillion kilometers. Blazars are a subgroup of quasars, which are objects propelled by supermassive black holes that consume gas and other material in the hearts of galaxies and emit two jets of particles in space in opposite directions. From our perspective on Earth, one of the two jets from blazars is pointed right at us. A new form of data is now available from space thanks to the Earth-orbiting IXPE satellite, a joint project between NASA and the Italian Space Agency. IXPE detects the average direction and strength of the electric field of the light waves that make up the X-rays, and the new data also includes the measurement of the polarization of X-ray light. Now, how are these jets powered? The most widely accepted theory for the formation of jets is that the charged particles in the fast-spinning acceleration disk will generate a strong magnetic field that will be in close proximity to the black hole. The field gets wound into a tight cone at the black hole's rotational poles if the black hole is spinning because it tugs on the field. In the process of accelerating particles away from the black holes as jets, this twisted field also absorbs energy from the black hole's rotation. Gisolini claims that the discovery that jets are so much more powerful than the acceleration disks demonstrates that the black hole spin must be involved, because disks alone cannot power the jets. Fabian admits that he still has slight reservations regarding the claim that the findings demonstrate the significance of black hole spin. He also suggests that it's likely the magnetic field is draining the acceleration disk's energy, making it appear less luminous. To determine whether the spin rate and jet power are related, Gisolini adds that the next step for science is to measure a black hole spin, but measuring it is quite challenging. According to Fabian, scientists have estimated the spin rate of a stellar-sized black hole created from just one or a few stars using NASA's NU-STAR X-ray instrument. It's perplexing that some of these tiny spinning black holes have jets whilst others do not, so even though there is growing evidence that black hole spin is driving jets, astronomers might not be able to prove it until they can measure the spin of a supermassive black hole. Gisolini believes that Europe's Athena X-ray Observatory will be able to complete the task, but he'll have to wait a while. Athena's launch is scheduled for 2028. And that is all for today's video. What do you guys think about the research? Are they useful? Share your comments in the comment section below. Thank you guys again for watching and for your continued support. Please like, subscribe and ring the bell icon for more videos. Also refer to other videos on our channel for more content, and we'll see you in our next video.